In section 10.5, we're going to continue to talk about using models to fit data and using those models to make predictions. But in this section, we're going to cover the topic of what's called a least squared regression line. You may already kind of know about this as the idea of what's called a best fit line. But in statistics, we typically refer to that as the least squared regression line. And before we get into your notes, I'd like to use an applet to kind of demonstrate why we call it the least squared regression line. So I'm going to switch over to this applet. And what this is showing us here is the relationship between foot length and height for 20 people. So you can see there's some data over here on the left, and we have a scatter plot over here on the right where they've plotted those points. And based on the scatter plot, we can see that there is a positive relationship. So people that have longer feet typically are taller. Now I can add in a movable line in this graph, and right now it's horizontal, and we probably wouldn't say that this line best fits that data. So to get it to fit better than it does right now, I would need to kind of drag some parts of those lines. So I'm going to drag the y-intercept down a little bit, and I can use this point to kind of slide the line up and down and adjust the slope. And, we can continue to adjust until we get a line that we think better fits that data than the horizontal line that they gave us. Now, another thing that I can do is I can click this button and it's going to then show me all the residuals. And we know that the residual is the difference between the actual data point, like in this case, that would be this point right here, and then the predicted value, which would be the point on the line. And in some cases, we have points above our line, which means they have positive residuals, and some are below the line, so they have negative residuals. And as I move this line around, the residuals change. Right. And notice if I move the line like this, now I'm getting some really big residuals because that line doesn't really fit that data at all. So our goal is to make the residuals as small as possible. We know, however, that when we look at these overall deviations, because we have some above and some below, that those positives and negatives will cancel each other out. And so to avoid that from happening, what we do is we want to square the residuals. So now I've turned all of those residuals into squares. And my goal is to come up with a line that makes the total area of those squares as small as possible. Again, notice if I drag my line like this, which is a line that we know doesn't really fit that data, I end up with really, really big squares. And I don't want that. I want the squares to be as small as possible. Now, the line that makes the sum of the areas of those squares as small as possible is what's called the least squares regression line. Least squares because it makes the squares as small as possible. So what I'm going to do is I'm going to turn these off just to make it look a little bit less cluttered. And now I'm going to show the regression line. And that regression line, the one that's in red, is the one that best fits the data. And that was pretty close to the one that I kind of eyeballed. So I didn't do too badly there. But this red line is the one that makes the sum of those squares as small as possible. So now let's go back to your notes and let's fill in some definitions and do a couple of examples. When a linear relationship exists between two numerical variables, the model that best fits the data would be an equation for a line. And because the best fit model would make the sum of the squared residuals as small as possible, we call this the least squares regression line. Now, LSRL is a very commonly used abbreviation, so we'll use that most of the time instead of writing out that full term least squares regression line. Now, the general form for what a least squares regression line looks like is this: y hat equals a plus bx. And you might notice that that looks similar to y equals mx plus b that you learned in algebra. In statistics, we typically use b for the slope instead of m, and we use a for the y-intercept instead of b. And the variable choice really doesn't matter, right? A variable is just kind of a placeholder for a number. Now, the little hat symbol above the Y is important because that is telling us that we are finding a predicted value for Y. Because we'll also have actual values for Y, and that's not what that symbol stands for. A is the Y-intercept, and then B is your slope. So how do we find the equation for the least squared regression line? Because remember, we don't usually want to eyeball it in statistics. We want to actually calculate what that value is and be very precise. So in this next example, I'll show you how to do that on your calculator. In example 1, we have a table showing the number of passing yards and points scored for each of the regular season games for the Lions in 2008. And I've also given you a scatter plot, and we've looked at this data before in earlier examples in this chapter. So we have passing yards in the top row. So those are going to be our X variables. And also notice that passing yards is on the horizontal axis. Points is on the Y axis. And so what we're going to do is we're going to put that data into the lists in our calculator. So that's what I did here. I put passing yards into list 1 and points into list number 2. And then what you're going to do is you're going to hit your stat button again, just like you did when you started your list, but you're going to use the arrow and you're going to scroll over to where it says calc. And then if you scroll down through those options, you'll notice that option number 8 right there says LinReg. That stands for linear regression, which is the same thing as least squares regression line. And you actually have two options that say LinReg, and really they do the same thing, but the second one, option number 8 there, is the one that's written in the form that we typically use in statistics, which is A plus BX. So I'm going to select that one. And then your screen might look something like this, depending on what model of calculator you have. You have to tell the calculator where your data is stored. So I have my X values in list 1 and my Y values in list 2. You can really use any list that you want, but those are typically the default ones. And then you don't need to put anything else in for the other options. If you wanted to, you could store your regression equation into the graphing functions under like Y equals, but we don't really need to do that. And you just go down then and you hit calculate, and then your calculator will show you something that looks like this. So notice it gives you the Y equals A plus BX form at the top. A, the first number that we're given here, would be then our y-intercept, 2.67955, and so on. And we're going to round that to 3 places. And then B is your slope, and we're going to also round that to 3 places. And then we get R. And we've used R before, so you're familiar with that. But now we know what these other numbers here are for. So we would write that equation like this. Y hat equals 2.680 plus 0.076x. Question B is asking us to use the equation to predict the number of points the Lions would score if they had a game with 225 passing yards. So 225 passing yards means that X is 225. So I can take that value for X and substitute it into my equation. And then if I calculate that, it will give me a predicted value for Y, which in this case is 19.78 points. And again, we know in football that they can't score 19.78 points, but we want to keep those decimal places just for accuracy's sake. Part C is showing you the scatter plot with the least squared regression line drawn in. And the question then is asking us here, which point would have the largest residual, and approximately what would that residual be? Well, we know that the residual is the distance between the actual point and the prediction at that X value, which is where the line is. So the largest residual would probably be for this point right here, because it seems to be furthest from the line. So that is the actual value, which I would estimate to be maybe about 20 or 21. The predicted value would be the spot directly below it if we just drop like a vertical line straight down on the line. So that's our predicted value for that number of passing yards. And the residual then would be the difference between them. So I would say the predicted is about 9 and the actual is about 20. So that means our residual would be the difference there, which would be about 11 points. And again, you're estimating. So if you estimated 12 or 10, it's okay. Now, how we interpret the slope and the y-intercept of the least squared regression line is what we have here next. So the slope in algebra we know is like rise over run, right? So it's telling us how much the y value is changing every time the x value increases by 1 unit. In statistics, we interpret that by saying the slope of the least squared regression line tells us how the response variable is predicted to change when the explanatory variable increases by 1 unit. So in our example for the Lions that we did, the response variable are the points scored, and the explanatory variable are passing yards. So we would say, to interpret that, when the Lions pass for 1 additional yard, their score can be predicted to increase by 0.076 points. So that's how we would interpret that. And notice I use the word increase here because my slope was positive and we want to indicate the direction. And this is telling us how much their score is predicted to increase when our explanatory variable, passing yards, goes up by 1 unit. The y-intercept in algebra is telling us where our line starts. In other words, where is the line passing through the x-axis or the y-axis? And the y-axis always has an x variable of 0. In statistics, we say that the y-intercept of the least squared regression line tells us the predicted value of the response variable when the explanatory variable is equal to 0. In this case, we would say when the lions pass for 0 yards, their predicted score will be 2.68 points. So again, the explanatory variable, passing yards, is 0, and we're looking for what our prediction for the y variable would be in that case. Here's a second example. We have data relating average drive distance in yards and driving accuracy. And we have also looked at this data set earlier in the chapter. And remember, this is just for the top 10 money winners from the 2009 LPGA Tour. I would recommend that you pause the video and go ahead and try the calculator steps on your own and see if you can come up with the equation and then also do the residual parts. All right, for part A, the equation for the least squared regression line rounding to 3 places would be y hat equals 2.163 minus 0.006x. And please remember to follow the directions about rounding. We're going to always go to 3 places and just follow the rules of rounding just for accuracy. Now for part B, if we use that equation to predict the driving accuracy for a drive of 255.5 yards, we plug in the 255 into that equation, and our predicted driving accuracy then would be 0.630. Now for part C, it says to calculate the residual for this point. Now what we're going to do to find the residual is we're going to look in our chart for a drive of 255 yards. And you'll notice right here, this golfer had a drive distance of 255 yards. Her accuracy was 0.733. That's her actual driving accuracy. Our predicted driving accuracy we got by using our equation. So the residual then is the difference between those values. So remember, we take the actual minus the predicted. And we were off by about 10% here. 0.103 is about 10%. So that wasn't a very good prediction in this case. Now, how would we interpret the slope? Well, the slope is how does the y variable change for every time the x variable goes up by 1 unit? We would say when a golfer's average drive distance increases by 1 yard, their accuracy is predicted to decrease by 0.006. And notice here, because we had a line that had a negative slope, we're predicting that their drive accuracy is decreasing. So you don't need to use a negative here. You would just indicate the direction by using the word decrease. And then for the y-intercept, we would say when a golfer's average drive distance is 0 yards, their accuracy is predicted to be 2.163. Now, this y-intercept doesn't really make sense in this context because, first of all, they're not going to have a drive distance of 0, and also their accuracy can't be more than 100%. And that happens sometimes. We just mathematically, the y-intercept works out to be something that doesn't make sense in the context of the problem, but that's okay. We can still kind of follow this format for our interpretation. Please do homework 10.5 in your assignment packet.